So, we will continue our discussion on the Paschen-Beck splitting. Paschen-Beck splitting, there is for intermediate magnetic field. So, if I compare this normal Zeeman effect and Paschen-Beck Zeeman effect, not effect Zeeman effect. So, Paschen-Beck effect. Okay. So, here just I have compared to the splitting of the spectral lines in case of normal Zeeman effect, and other one is Paschen-Beck effect. Okay. So, normal Zeeman effect, here it was very high magnetic field or spin orbit interaction coupling was negligibly small or vanish. Okay. So, there what was the energy expression for spectral lines. So, del E equal to E n dash minus E n plus mu b b del m l plus 2 mu b b del m s. So, here I have written. So, but basically I do not need this term, because only transition is possible when del m s is 0. Okay. And in case of Paschen-Beck splitting, what happens? So, this del E equal to the same one. Okay. So, same one I have written, del m s I have not written here, because I do not need here itself. So, plus an additional term we have got for intermediate magnetic field, okay, because this LS coupling was not neglected in this case. So, now if you see splitting, so let us take two energy level, Ns means L equal to 0 and N dash P, where L equal to P, L equal to 1. Okay. So, two energy level. Now, this energy level before applying magnetic field, what will happen? So, if there is a transition is permissible, allowed, because del L equal to plus minus 1 in this case, either plus 1 or minus 1, whatever does not matter. So, without applying magnetic field we will get one line, one transition. Now, what happens after applying magnetic field? After applying magnetic field, what will be the energy? Energy is here I have shown. Okay. So, E n means this is the E n energy before applying magnetic field. Now, after applying magnetic field, these the things we will see. So, this E n plus that term, okay, that term mu b b del m l. So, del m l means here you can tell this energy term, actual energy terms I have to show you. Actual energy terms was E n plus m l mu b plus 2 m s mu b. Okay. So, whatever delta m l we have written, that basically m l dash minus m l. So, both m l dash and m l is there. So, this m l equal to 0 here, L equal to 0 means m l equal to 0. So, m l equal to 0. So, there will not be any energy change. So, this is there for m l equal to 0, this is there, and then due to m s term, 2 m s, right, 2 m s then into mu b, 2 m s then into mu b. So, that will give you the for m s equal to plus half and m s equal to minus half, 2 m s means plus 1 and minus 1. Okay. So, there will be symmetrical splitting of this one. So, one is this whatever the original energy plus mu b, and whatever the original energy minus mu b. So, that is coming 2 m s mu b. Okay. So, m s is plus half and minus half. So, this splitting we will get, and then for next one L equal to 1. So, m l will be plus 1, 0, minus 1, right. So, now when m l is plus 1, so energy I think I should write what is the energy E equal to energy was En plus ml plus 2 ms, okay, and then mu v. Okay. So, then it will be easier for me to explain. So, now you see this now for ml equal to plus 1 0 minus 1. Okay. So, ml equal to 0. So, there is a, so energy will remain En, okay, or En dash whatever. So, this for ml equal to 0. So, ml equal to plus 1 and minus 1. So, it is mu b. So, that is mu b into b, that is magnetic field, and this Bohr magneton. So, here you will get this whatever the original energy now plus mu b, and other one for minus 1 it will be minus mu b. So, now this line is splitted into 3 lines, okay. One is original energy, other is mu b higher, and other one is mu b lower. Okay. Now, for each case, so when ml equal to plus 1, this is the energy. Now, for ms again 2 ms is there. So, ms equal to plus half means this energy will increase by mu v plus mu v. So, energy increase by plus mu v, and other one minus ms, energy will decrease by minus mu v. So, this minus mu v. Okay. Similarly, for each case plus mu v minus mu v from original energy, for this also plus mu v and minus mu v. So, this energy separation here, energy separation are basically mu v b, okay, between the successive energy levels. This all are this energy separation. That is why I told that this energy splitting it has symmetry. Okay. Now, here if you see this considering the transition rule, del ml equal to 0 plus minus 1 and del ms equal to 0. Okay. So, now if you consider that transition, okay, if I consider this one here. So, from here if I start from here, okay, that means if I start from here, I think I will take another pen. If I start from, let me check. Okay. So, in this case only if I consider this energy splitting. So, here I can see this transition from this line to this line, it is allowed because delta ml in this case this is 0 and this is minus 1. So, it will be minus 1 or plus 1 whatever. So, this is allowed. Okay. From here to here also allowed, del m will be 0, and from here to here also allowed because this is plus 1 and this is 0, this means that means that del m will be plus or minus 1. So, it depends, you are taking difference from final to final one minus initial one. So, generally final one minus initial one has to take. So, if you set that rule, so in one case it will be plus 1 and another case it will be minus 1. Okay. So, these 3 terms. So, as if I will get 3 lines in this case. Now, if I consider this ms, del ms equal to 0, then for each line if we consider this line. So, this line now it has 2 energy level, okay, and here also it has 2 energy level. Now, we consider for these lines. So, if I consider this, so from here to here it is allowed, del ms has to be 0, okay, it is allowed, but here to here it is not allowed. Okay. So, in this case if it is plus ms equal to plus up, so this case also ms equal to plus up. So, del ms will be 0 for this case. If it is ms equal to plus up, so other one will be minus half, then ms plus half to ms minus half. So, del ms change will be plus 1 or minus 1. Okay. So, that is not allowed. So, from here to here it is not possible. So, similarly for ms equal to minus half, this one is ms equal to minus half. So, m is equal to minus half to m is equal to minus half is possible, m is equal to minus half to m is equal to plus half is not possible, okay, because del m s. So, wherever this, so m s dash equal to m s, so there only transition possible, other case transition is not possible. So, here just one example I gave you. So, in this case this one line, now considering the spin magnetic moment, considering that means m s. So, considering that one, so we are getting basically two lines, okay, but these two lines, the energy of these two lines are same. If you see this symmetrical break, because from here you see this whatever the difference of energy. So, now additionally in one case whatever, so here I can see that for these lines what happens. So, this mu b, so it has gone up by mu b, and for this one also it has gone up by mu b. So, these lines, energy of this line is basically same energy of this line. In other case also one can tell that, okay, whatever the energy, it has come down by mu b, and this line also whatever energy, it has come down by mu b. So, both has come down by mu b. So, energy difference is same as this energy difference. Okay. So, basically these two line is nothing but the same this line. Okay. So, but transition wise it has two lines, but energy are same. Similarly, for other two lines one can show that we will get two lines, but their energy are same, and this case also these two lines, but their energy are same. So, basically we will get in strong magnetic field we will get basically only 3 lines, whatever these 3 lines we will get 3 lines. Okay. So, that is normal Zeeman effect. Now, in Paschen-Bach splitting there, so this term is there. So, that means this type of splitting will be there. Now, in energy level additional term is added, and that term depends on L value, you know, and ms value. Okay. So, whatever the symmetric was there, now this term is contributing some additional energy, and thus yes. So, and this term is not basically is not symmetric term, okay, because this lambda n dash L dash is not same as lambda n L, because in this expression n and L are there. So, here this lambda n L and lambda n dash L dash, these have different value, okay, and it depends on L and n also. Okay. So, this change of energy here this asymmetric. Okay. So, that is why. So, but these are small term, it is not very it is comparative to this term. So, this change of energy will be small, okay. But so this will break the symmetry of this energy splitting, and so there will be asymmetric break of this energy level, asymmetric break of this energy level. So, then because of this asymmetric break of the energy levels, but transition rules are same. So, earlier whatever these two level was having the same energy, now their energy will not be same. So, but they are closed, these two value energy value will be closed. So, that is why we tell this we will see this doublet. So, each line whatever 3 lines was observed in normal Zeeman effect, in Paschen-Bach effect. So, each line will be will form doublet, okay, closely spaced 2 lines we will get. So, here basically we will see 3 doublet, instead of 3 lines 3 doublet means it is we will get 6 lines. Okay. So, so this is called Paschen-Bach splitting. So, normal Zeeman effect, it is basically for high magnetic field, LS coupling is vanished or negligibly small compared to the magnetic interaction term, okay. And in Paschen-Bach effect this magnetic interaction term is higher, but but it is comparable, but this LS coupling term also comparable is small, but it is close to the LS coupling this magnetic interaction term, and because of that. So, this asymmetry splitting of the energy levels. So, that is why the degeneracy basically removed, and we get each line whatever normal geometry each line. So, it will show as a doublet in in intermediate field, and that is called the Paschen-Bach effect. Okay. So, next I will consider the if magnetic field is very is weak, is very low. That means, third case 3 is weak magnetic field. Okay. In this case, whatever Zeeman effect we will see, that is called the anomalous Zeeman effect. Okay. So, now magnetic field interaction term, as you know, this is the magnetic field interaction term and this term is now very small, it is small compared to the LS coupling term. Okay. So, how small, how big, that we have to compare with some other reference. So, here reference is the spin orbit interaction term. So, spin orbit interaction term, in case of normal Zeeman effect, we have seen that spin orbit interaction term is very small compared to the magnetic interaction term. So, this can be neglected. For intermediate magnetic field, we have compared this magnetic interaction term with this spin orbit splitting interaction term, and we have considered that still magnetic interaction term is higher than the spin orbit interaction term, but this time this term is smaller, but it is close to the magnetic interaction term. Okay. So, we cannot neglect, we have considered. Now, third case, in case of weak magnetic field, we are telling that this term is higher than the magnetic interaction term. Now, we see this term is higher, and other term in Hamiltonian, this relativistic correction term, Darwin term, earlier we have neglected that one, because these are the smaller than the LS interaction term. Now, earlier we have neglected LS term, it was very small. So, other term we neglected, but now whatever the magnetic interaction term, so that term is really very weak. So, compared to that, this LS coupling term is strong, we are considering. So, now we cannot neglect this relativistic term and Darwin term. Okay. So, unperturbed Hamiltonian, so that is basically Dirac Hamiltonian we have to consider. So, this H 0 plus this H dash LS plus H dash relativistic correction term plus Darwin term. Okay. H G dash. Okay. So, this let us consider this is H 0, this H 0 is Dirac Hamiltonian. H 0 we are writing as a for representing the unperturbed Hamiltonian. Okay. And this other perturbed Hamiltonian is this interaction term, because perturbed term always has to be small term, okay, correction term. So, now it is our perturbed term. Okay. Now, this is now nice, because we have to know the solution of the unperturbed term. Okay. So, this is the Dirac Hamiltonian. So, we know the solution. What are the solution? E n j energy equal to E n 1 plus z square alpha square by n square n j plus half minus 3 by 4. So, this solution energy is known to us, and corresponding wave function psi n l j m j was the eigenfunction. Okay. And this eigenfunction was for, we know, we have checked earlier, see earlier, that is a H 0, L square, A square, Z square, J square and J z. Okay. So, this wave function was the simultaneous wave function of this operator, but it was not the wave function of Lz and Hz. Okay. So, this is important if Lz and Hz would be the this psi NL JMJ wave function of this Lz and Hz, then just from eigen equation one could get the eigenvalue. So, but unfortunately this not the wave function for Lz and Hz. So, in our interaction term Lz and Hz is there. So, for this we cannot use this psi n L J M J as a eigenwave function. So, we have to basically follows the perturbation method to find out this value. Okay. So, how to that correction term, how to find out that, you know, this in Dirac notation I have written. So, this is basically psi N L J M J, then this H B term, H B dash Hamiltonian correction term, okay, or perturbation term, and then this psi N L J M J. So, this in Dirac notation we have written, and one has to find out how to find out that that one has to know. So, now H B dash if you put H B dash if you put this the term. Okay. So, I will get E B by 2 m L Z yes. So, here I have written, so H B term, since this psi N L J M J is not the wave function for Lz and Hz. So, we have tried to convert it to Jz, because it is the wave function for Jz. So, Lz plus 2 Hz. So, Lz plus Hz can be written as Jz plus Hz. So, that is why we have just modified this one in terms of Jz plus Hz. So, now for Jz it is so this eigen value will be, if we apply on this wave function, it will give m h cross. So, that is why E b by 2 m h cross m j h cross j m j h cross plus mu b b by 2 m. Now, we have to find out this expectation value basically for Hz, expectation value of Hz, and one has to do that. I have not done because I am trying to avoid this details calculation, because for that really students should know quantum mechanics. So, but I am just showing the result, so that student later on when they will complete their quantum mechanics course, so they will be able to fill up the gap, means they can just calculate how this is giving this value. Okay. So, if you calculate this expectation value, so it will come m j h cross j plus 1 plus s plus 1 minus l plus 1 divided by 2 j plus 1. Okay. Now, here mgh. So, E b by 2 m, this common term is there, if you take common. So, you will get basically 1 plus this term. Okay. So, that is why we have written here. So, that E n j m j is equal to E n j plus m j g j mu b b. Okay. So, yes. So, g j is basically 1 plus j plus 1 plus s plus 1 minus l plus 1 by 2 j plus 1, as I mentioned earlier. So, basically as I told you, from here if you E b by 2 m j h cross, if you take common, so then you will get 1 plus this one. So, that is what we have got, and this one we have written as a g j. So, Gj, Mj, mu b b. So, our now in weak magnetic field, the energy, what will be the energy of the energy levels? So, that is this. So, it's this equal to Enj without magnetic field plus Mj, Gj, mu b b. Okay. So, now you consider these two energy level, say S half and P half. Okay. S half and P half, because now this we have to consider this because it energy depends on J, not L, right. So, because energy expression it does not depend on L, so it depends on J and N. So, we have to use spectroscopic term or energy level for J value. So, J equal to half. So, S half, L equal to 0, J equal to half, okay, and L equal to 0, P and J equal to half. So, now between these two line, so L is 0 and L equal to 1. Okay. So, transition is possible before applying magnetic field, this transition is possible and it gives one spectral lines, okay, because it fulfill this selection rule del L equal to plus minus 1, right. Now, see that now this for additional term, so it will be splitted into 2, because Mj value will be, if J value is half, Mj value will be plus half minus half. So, plus half and minus half you will get the energy, and plus half and minus half, here you have to see Gj term is there. So, that term depends on J, S, L. Okay. So, for a particular J and for a particular S, this level L also same. So, for this level the Jj term will be same. Okay. Now, depending on the Mj value, so it is splitted into 2, it is split in, because here L equal to 0. Now, for L equal to 1, this one L equal to 1. So, here also we will get for Mj, J is half. So, Mj will be plus half and minus half, again we will get 2 splitted line. Now, here imagine that because of this Gj, so this splitting will not be symmetric, okay. It will be asymmetric. Symmetric means with respect to this original one. So, it is by same amount it is going up and by same amount it is going down. So, that we call symmetric breaking, symmetric splitting. Okay. But in this case it will not be symmetric splitting, Okay. So, that is why whatever considering this selection will del J equal to 0 plus minus 1. Okay. Considering this one, this fourth transition will be possible, considering the J value. Okay. So, and due to asymmetric splitting, all 4 lines we will see, otherwise this if it is symmetric. So, energy of this could be the same energy of this one. Okay. If it is symmetrically splitted. Okay. But due to Gj term it is asymmetrically splitted. So, the energy of this one will be different than this one. Okay. So, we will get this 4 splitting, okay, from one line split into 4. Similarly, so this the it may be hydrogen line, or it can be sodium D1, sodium D1 line we get from P half to S half, and D2 line we get 3 by P 3 by 2 to S half. Okay. So, this sodium D2 line. So, sodium D1 line will be splitted into 4 lines, and sodium D2 line will be splitted into 3 lines, not 6 lines. Again here this S half is splitted into 2, S, this is P 3 by 2, J is 3 by 2. So, M j will be 4 value plus 3 by 2 plus half minus half minus 3 by 2. Okay. So, it will give 3 4 value for 4 M j value, and G j will be also different because there one has to calculate this one. So, that is why this it will not split it symmetrically, it will split it asymmetrically, and that is why here whatever the transition is possible. So, here one can show that these 6 transitions is possible, okay, considering del M j equal to 0 plus minus 1, 6 transitions is possible. So, this one line before without magnetic field will be split into 6 lines. Okay. So, in anomalous Zeeman effect in weak field, this splitting is one energy level split into more lines. Okay. So, this is the basically anomalous Zeeman effect, already I have explained earlier. So, now sequentially using the quantum mechanics how things are coming, that I have discussed. Now, I think I will stop here. Thank you.